Alrighty, morning everybody. That includes you, Lydia. And Hi, Lydia. And welcome back to Galois Theory. Plan for today. We're going to finish our discussion of UFDs, unique factorization domains, including our second half of our proof that all PIDs have to be UFDs. And then we're going to talk about some polynomial stuff. I've got my usual office hours today, 1 to 2. Tomorrow, 11 to 11:45. And Monday, 11 to noon and 1 to 2. Don't forget, homework 2 is due today in class, as it says on Canvas, very clearly. In class, due. But as long as you get it to me by the end of today, I'll be fine. I just felt the need to point that out for the slackers in the room.
I am not a slacker.
Lydia, I don't know if you submitted it yet, so
There are a scary number of people in the front row who have not turned in the.
Yeah.
I turned it in.
Okay. Also, homework 3 is posted. It's on Canvas. It's due next Thursday. It also says in class. So don't hurt me so. Any questions or comments before we get started for today? Here's a oldie but a goodie. What do you call a number that can't sit still? You call it a Roman numeral.
I feel that piercing my skull.
Oh, see, my 105s love that one. It's like one of them said it was their favorite one of the semester so far.
That one in my bone.
So last time we talked about a few different things. We talked about 2 different types of rings. One being a UFD, a unique factorization domain, where the whole idea behind a unique factorization domain is if you're given it's an integral domain, where given any non-unit A in your domain, meaning anything that doesn't have a multiplicative inverse and that also isn't 0, you can write it as a finite product of irreducible elements. And moreover, we say that this factorization into irreducible pieces is unique in the sense that if you have 2 different factorizations into irreducibles, then they have to have the same number of irreducible terms, and you can reorder these terms so that every term in the first factorization is a unit multiple of a term in the second factorization. So the idea being in something like the integers, which form a UFD, where units we said were, oh sorry, you can't see this, Lydia, plus or minus 1, you could factor something like 6, for instance. You could factor it as 2 times 3, or as like -3 times -2, or 3 times 2, or -2 times -3. But any which way you factor 6 into irreducible terms, which over the integers are the same as the prime integers, there's always going to be 2 of them, and there's always going to be a way to sort of correlate terms from the first with terms from the second so that each is a unit multiple of the other. In this case, 2 and -2 are a unit multiple of each other, 3 and -3 are a unit multiple of each other. So there's an invertible way, in other words, to go from a irreducible term in one factorization to irreducible term in the other factorization. So we spent some time looking at that last time. We also talked about Noetherian rings. You after Emmy Noether, early 1900s mathematician, who, with the idea behind a Noetherian ring is that whenever you have a chain of ideals that keeps getting bigger and bigger and bigger forever in your ring, I1 being a subset of I2, being a subset of I3, being a subset of I4, etc., etc., eventually you have to reach the whole ring and you can't keep getting strictly bigger. So eventually you'll get to a point, some I sub n, where for any k past the nth one, I sub k and I sub n are just equal to each other. Again, example being something like the integers. Where in the integers, you can make a chain of ideals, something like ideal generated by 8 is contained in the ideal generated by 4, is contained in the ideal generated by 2, is contained in the ideal generated by 1, And then you can't get any bigger than the ideal generated by 1, so if you want this to keep going, you have to just keep using the same ideal forever. Plot twist, -1, but it's the same ideal, so it's not actually any different. And what we proved at the end of class last time is that all PIDs, principal ideal domains, where ideals are generated by a single element, have to be nitharian. The idea being in a PID, if you have this sort of chain of ideals, you just take the union of all of them, show that that's an ideal. Since it's a PID, it has to be generated by a single element, which has to be in one of these ideals, and then whichever one of these ideals it's in, that ideal is the biggest one in your chain. Can't get any bigger past that point. And that's where we left off last time. Any questions or comments before we move on to the new stuff? So this is something that we're going to use as a lemma today in order to prove the results I actually care about a little bit more, which is that all PIDs have to necessarily be UFDs. And this is kind of our last major result in fact. So in other words, if you're working over an integral domain where every ideal can be generated by a single element, then all non-units have a unique factorization into irreducible elements. Or again, irreducible just means you can't break it up into two factors unless one of those factors is a unit. That's a mouthful. All right, y'all ready for this? I'll give you a hint. We're going to be using all PIDs or nitharian a lot. Here we go. So we're going to let R be a PID. And we're going to let A not equal to 0 be a non-unit in R. And first thing we're going to do is we're going to prove our first bullet point here that we can break A up into a product of irreducible terms. A finite product, I should say. There's a finite number of irreducible terms in your ring that will multiply to give you an A. So here's how we're going to do it. Assume A is irreducible. Then we're done. A equals A. Great. Everyone okay with that? All right, proof complete. Well, no, we just need to eliminate that case first. So if A is itself irreducible, we're done. So assume A is irreducible. Unirreducible. A irreducible? It's reducible. So somebody remind me, what does it mean to say that an element A is not irreducible? No?
It can be broken up into some finite group of irreducibles that are non-units.
Oh, we can break it up into a finite product of irreducible terms. Oh, great, then we're done, because that proves that's exactly what we need to prove in the first bullet point. Wouldn't it be nice if we already knew we could do that? Well, we can, but we need to prove that. We don't know we can.
Right.
Isaac?
Strictly speaking, it just means that you can break it up into two non-units.
Yeah, then you can write A as the product of two non-units. Those units may or may not themselves be irreducible. If they are, then that's nice. So I'm just going to say then A has a non-unit divisor A1 with A equal to some A hat times A1 for some A hat in there.
Why not just A2 times A1? Why A hat?
Because A2 I'm going to be using to refer to something else here in a second.
Also because hats are silly and we like to wear them.
Exactly. And what do you have against hats? What did your local haberdasher ever do to you?
Lead poison.
Lead poison. I mean, depending on when and where you are living, yes, that is very likely.
I thought Mercury poison.
Is it Mercury? Oh, it's Mercury. It's
Yeah.
Mercury.
I mean, that's why you have like.
Yeah, Mercury poison.
It's all Mercury in my head.
Regardless, Emily Rose, to actually answer your question, we have a different A2 in mind here in just a second that we're going to be using to build a whole chain of A sub i's.
Pretty close to flat.
A whole chain.
Let's call it.
So A is a non-unit divisor A1 with A equals A hat times A1 for some A hat. Well, then, either A1 is irreducible, or A1 has some non-unit divisor A2. What does that mean? Well, that means we can write A as being equal to A hat times some, I don't know, A double hat A2. You get, hopefully you kind of see where this is going. Basically, what we're going to do is we're going to keep taking A and saying, hey, we either have an irreducible factor or we get something that's not irreducible. And if it's not irreducible, then that means it's going to have some other non-unit factor that we can pull out of it. In this way, assuming none of the A sub I are irreducible, what do we know? We know that we get a sequence of divisors A1, A2, A3, ... where each A sub I divides the A sub I that came before it.
Well, you probably already explained this, but those are the same A, right? What? No, up a line. The divisor is. Oh no, those aren't commas. Okay, that's A1.
Oh, this is,
Yeah, and it's worse the whole line above.
gotcha. Oh, yeah, just you wait until just you wait. You're gonna have a hard time reading my notes, I know it. So we're gonna get a sequence of divisors A1, A2, A3, where each A sub I divides is a divisor of the one that comes before it. Yes.
On line 2, is that supposed to be A sub, not line 2, line
This
5,
line?
it's line 5,
This line?
yeah. You have your arrow and then your A, well I guess that's
A hat times some, so this is A1, and we're basically saying A is A hat times some A1. Well,
okay.
either A1 is irreducible or A1 has a non-unit divisor A2,
I see.
and we can break A1 up into something from our ring times A2.
Okay, that makes sense. Okay.
So each A sub I is a divisor of the one that comes before it. Where do you think we're going with this?
It has to stop somewhere, so it can't be indivisible.
Why does it have to stop somewhere?
Well, or it has to repeat itself at some point.
Why?
Because you get to a unit at some point.
Why? There's no reason in theory why we can't keep going forever. Except for the fact we're working in an Ethereum ring, necessarily, because it's a PID, which means if we happen to have some chain of ideals, it would have to eventually stop. So how can we build an ascending chain of ideals out of this?
You just generate with the AIs.
AIs. Yeah, just take the ideals generated by the A sub i's.
It's a PID, so we know we got ideals.
Oh, hey. Well, I mean, even if it's not a PID, we could do this part.
Yeah, it
But
makes
the
it
fact that
really-
it's
makes it real nice.
then we get a chain of ideals. Ideal generated by A, properly contained in ideal generated by A1, properly contained in ideal generated by A2, or not properly, but is a subset of ideal generated by A2, etc., etc. We're going to get an ascending chain of ideals. The idea being, since A is a multiple of A1, anything that's a multiple of A also has to be a multiple of A1. So A1 being a divisor of A means ideal generated by A is a subset of ideal generated by A1. And similar for the rest of it. A2 divides A1, so anything that's a multiple of A1 has to be a multiple of A2, ... Rinse and repeat. Questions or comments thus far? Well, we're working over a PID.
You don't.
You what?
Dr. Wallace not just got fired with the dog.
Oh yeah, there's multiple dogs in the department now. You didn't know? Well, we're working over a PID. And Isabel, what did we prove last time about PIDs?
They're an Ethereum.
They're an Ethereum. And since our ring is an Ethereum, what do we know about a chain of ideals that's getting bigger forever like this?
And
It has to end, or it has to, at some point, stop getting bigger at the very least. So we can say, since R is an Ethereum, as a PID, this chain must terminate at some, I'll call it A sub k.
not A sub n.
A sub k. That's what I wrote in my notes and I'm sticking to it. As otherwise, that would break the, well, I'm just going to say that. This chain must terminate at some A sub k. Because otherwise, that would break the Noetherian condition that says chains can't keep getting bigger forever. So, our ideal generated by A sub k can't get any bigger. What does that tell us about A sub k specifically?
I want to say it's the whole ring, but it could be, I think, maximal too, so.
Yeah, well, assuming each of these A sub k's are non-units, it's not going to generate the whole ring.
Okay.
Yeah.
So it's just maximal.
It has to be maximal ideal, or the ideal generated by A sub k has to be maximal. And what do we know about ideals generated? If an ideal in a PID is maximal, what do we know about the thing that generates it?
It's irreducible.
It's irreducible from the theorem we had on page 2 of this packet, for those of you following along. Thus, and then we can say, since A sub k is not a unit, we know the ideal generated by A sub k is maximal. Hence, A sub k is irreducible. Yay! What did we actually just prove?
Eventually you get to an irreducible when you factor out A.
Eventually you get to an irreducible.
For one of them.
Eventually you have one irreducible factor.
Uno.
Oops.
You should be able to do it for the rest of the hats, but that's going to take a little bit of showing.
Well, not really. We're just going to say repeat this whole process as many times as you need to. So, what do we know from this? Well, we know, goodbye definition of UFD. I'm going to regret erasing you, I know it, but
That's fine.
I'm going to give, you know, because of, oh, because it upset you so much, Emily Rose, I won't call it a sub k anymore. I'm going to give it a new name. I'm going to call it z sub 1.
Excuse
Right, you
me?
can't, no, but that's hurting
A
the
capital Z?
Should we just go through
Lowercase z.
Should we just go through the whole
That's
thing
more
except for the A's and K's or first K?
That's capital is weird.
Thus, if we let a,
Yes.
I'll say if z sub 1 is equal to a sub k, we know a is going to be equal to z sub 1 times b sub 1 for some irreducible z sub 1. And b1, we don't know anything about. Just that it's some element in our ring. Oops. Well, we have not shown that we can write this as a finite product of irreducibles because we've shown that it has one irreducible factor, but we don't know if b1 is irreducible. If it is, then we're done. But assuming it isn't, then we do again to write b1 as a product of some irreducible z2 times some b2. So if, yeah, exactly, it is a recursive proof. We're actually going to just say, well, the same logic, because I'm not repeating all that again. So I'd say if b1 is irreducible, we're done. Or a unit for that matter. If b1 happens to be a unit, well, then that just means z1 times a unit is still irreducible. So we'd still be done that way too. So otherwise, we could say by the same logic, b1 is going to be equal to z2 times b2 for some irreducible b2. Z2, excuse me. Oh, technically that's true, but I want the z's to be the irreducible terms. Basically, I'm saying if b1 is not irreducible or a unit, then just go through this to here again, replacing a1 with b1, and you can similarly write b1 as a product of irreducible term times something else from your. Yes, Lincoln.
This doesn't, this wouldn't be true for later iterations of, doing all that again. But in the particular case of B1, it couldn't be a unit, right? Because otherwise A would have to be irreducible.
Yes.
It doesn't change anything because it's just.
Yeah, that's true. Yeah, that's true. B1 can't be a unit, otherwise we would have stopped like up here. Yeah, it doesn't, you're right. It doesn't actually change anything, but B1 can't be a unit because we assumed A is irreducible. A is reducible, excuse me.
Do we know it terminates? This whole thing terminates?
Oh gosh, I don't know. Maybe we can build a chain of ideals from this chain of ideals and see if that terminates somewhere. That's why I said this proof gets a little bit messy. I did not want to have to do this one out loud.
Well, it makes a lot of sense.
Just to make it clear, that means we can write A in the form Z1, Z2, B2.
Oh, yeah. And so
Rinse and repeat.
I already wrote that in my notes.
You did.
Yes.
Okay. If this process never ends, what do we get? We get a chain. Where the ideal generated by A is a proper subset of the ideal generated by Z1, is a proper subset of ideal generated by Z2, is a proper.
What? Wait.
Where literally going from one step to the next in the chain involves repeating this whole argument again.
but
But why is
if Z1 is irreducible,
Then how can it be the subset of some other ideal?
Oh, it's because I wrote Z's when I meant to write B's.
Okay.
Okay.
Yeah, good call. Yeah, these things are probably not irreducible, because if they were irreducible, we'd stop there. Yeah, good call.
Are they properly contained? Does it matter?
They have to be, because B2 is not a unit multiple of B.
Right.
It's
just
B1 based on these things that have irreducible factors to them. I'm gonna erase this. So we get an infinite chain, which can't happen since R is a variable. Thus, this process has to stop at some point. What does that mean? Well,
It's fine.
it means it's finite. That just means at some point one of the b sub k's has to be irreducible itself. Because this process being able to continue forever only occurs if the corresponding b sub k isn't irreducible, meaning we can factor that into smaller terms. Thus, for some irreducible I'll call it b sub k plus 1, we can write A is equal to z1, z2, up through zk, b sub k plus 1. Which, since all the z's are assumed to be irreducible, and the b sub k plus 1 is irreducible, means we can write A as a finite product of irreducible terms. Boom. So that proves that we have the less complicated bullet point of being a UFD satisfied. Because we still haven't shown anything about uniqueness. Any questions or comments thus far? I'll be honest with you, I don't want to prove uniqueness part of it. It's in the book, it's tedious, it's annoying. I wanted to show part of this proof because I want to kind of show how is this ascending chain condition being used. But the uniqueness part is just look. I feel like it. We all okay with that? Andrew's okay with it, so I'm okay with it. Okay, phew. Just proving the fact that there is a way of writing K as a product of irreducible terms is complicated. So what do we know from this? Well, we've now completed our diagram of things that lie between fields and integral domains. So it's on the next page. So I'll just say it's a corollary. I'll write this out with the diagram, but as a corollary, every field and every Euclidean domain also has to be a UFD because all fields are Euclidean domains and all Euclidean domains are PIDs, and we've just shown that, well, we've shown that all PIDs are UFDs. So we got this nice diagram. Field implies Euclidean domain, which implies PID, which implies UFD, which implies integral domain. This is what we've found at this point.
Which implies ring.
Say what?
Which implies ring.
Which implies commutative ring with unity,
Yeah.
which implies commutative ring, which implies ring. If you really want to get this. Actually, chair of the, well, he was chair of the math department at Iowa when I was a grad student there. His whole research area was finding new classes of rings that lay somewhere in between these classes. Like UFDs that satisfied some other conditions but still couldn't be said to necessarily be PIDs, for instance. I was going to do research with, he was going to be my advisor, but then he got cancer. And he was given like a 10% chance of survival. But since he was a tough, hoary old guy, he survived and is now doing research again with students. That is getting far-fetched, but that's what you made me think of. So, turns out none of these are equivalences. For each of these, that we can find an example of something that's in this one but not that one, this one but not this one, this one but not that one, this one but not that one. PID but not Euclidean domain, was the one where we had to get messy and say like, do like that. That was our PID, that was not a Euclidean domain, that's really annoying and hard to prove. What would be an example of a Euclidean domain that's not a field? That one's not as bad. The integers! Lincoln?
I was gonna say Gaussian integers.
Gaussian integers, yeah, would also work. You could say Z, or the Gaussian integers, or, for instance, real polynomials, or remember today, any polynomial ring over a field. We've seen lots of examples of Euclidean domains that don't form fields. What about a UFD that's not a PID? We've seen an example of that. I don't know if we've explicitly said it's, well, yeah, no, I did explicitly say on Tuesday that it is a UFD.
Is it RX?
Oh, RX is here,
Somewhere down there.
but it's close.
Something, yeah, something related to RX.
It is something related to RX, and it's a subring of RX.
Like, ZX.
ZX!
Yeah, there it is.
QX would also be in this category still. Yeah, integer polynomials give us a nice example of a UFD, where integer polynomials form a UFD essentially because the integers do. But they're not a PID because, as we've seen, if you take, for instance, ideal generated by 2 and x in the integers, that gives you an ideal that can't be generated by a single element.
Does it have anything to do with the finiteness of the units?
The fact that the integers have a very small number of units is very relevant here, yes.
Oh, okay.
Compared to Rx or Qx, where there's infinitely many units to play around with. Or Cx, for that matter, would also fall here, but not here. All right, how about a UFD that's not, or how about an integral domain that's not a UFD? I don't know, how about, I thought that one.
Oh.
Why is that? That's on homework 3, proving that that does not form a UFD. Oh yeah, it shouldn't be too hard,
No.
he says.
You should make it-
At least it's better than,
Wait, so what about -2?
bracket.
What about what?
One
Two
is
plus
square root of negative.
No, now you gotta
2.
prove that one, yeah.
It's negative.
Just let that be on the final.
Z adjoins square root of -2,
Yeah.
you mean? That would, same category. Z square root of -p for any prime p would also be in the category.
Oh, that goes a lot, that's supposed to be.
Or Z adjoins square root of, I think, but I'm not 100% sure on this one. I think Z adjoins square root of -n for any square free n. I
Square
think falls in that category.
What would
That's
happen
not
if you
what
did a
it's square
square
root
root?
of.
What would it fit in?
Madness.
Oh.
So, transcendental,
Negative.
Z adjoint transcendental would go here.
Oh, okay. Oh, that kind of makes sense, yeah, because the I.
What if it was, like z adjoined square root of -5?
Well, I'm not going to spoil too much because these are sorts of questions we're going to be looking at a lot as the semester goes on. Andrew, you look unhappy about something.
No, I was just thinking like what would it look like to add transcendentals to Z.
Trust me, we're going to explore that in thorough detail. Although we're more so going to be doing that with adjoining them to Q, but than the integers, but similar sort of idea. So, yeah. So homework 3 has 2 questions on it.
Oh.
I don't remember what question 1 is off the top of my head. Question 2 is proving that this is a integral domain that's not here. Right? This being an integral domain is not hard. This not being UFD, you just have to find a factorization. Here, I'll give it to you. Because I give it to you in the homework.
Okay. Oh, that's very strange.
That's 2 different factorizations of 4 into irreducibles. And in the homework, you're going to prove that A, these things are all in fact irreducible, and B, neither of these are a unit multiple of 2. So we have 2 distinct factorizations where it doesn't just come out to terms in one or unit multiples of the other. But I outlined that. I outlined in the homework how to do all that. Any questions or comments? Is that a... Okay. All right, so that's it for this stuff now. So what are we going to be doing from now on? Polynomials, and more polynomials. Woo. Most of the rest of the semester is going to be about stuff happening in various polynomial rings. Or seeing what happens if we take Q, adjoin something like, I don't know, either transcendental or something like square root of 2 to it, and seeing what sorts of properties does that have, and how does that sort of somewhat behave like a polynomial ring. So that's impact time. Oh. Can always count on Seamus for a creepy
That was
straight.
perfect.
That was just.
Oh, that was
That was
perfect.
perfect.
I can usually. Well, I can't always count
We're
on
just
Seamus
sitting
too.
near
I was distracted.
We were sitting near each other.
No, that was what made me laugh at it so much. I'm used to it coming from Seamus.
There's my quizzes from this morning. I knew I had written out more quizzes somewhere.
It's because we sat near each other in quiet, that's why. That was so simple.
Yeah, I ran out of quizzes passing out of my 105 class this morning, and it was embarrassing.
Oh.
Did people ever share quizzes?
No, I just printed out a couple more. I was only down like 2, but
Now that you found them, are you going to give them out to them?
say what?
And now that you found the extra quizzes, are you going to distribute them to them?
No, because I just printed out more for them. I'm not going to actually just. I don't know. Do you all want to take a 105 quiz?
Yeah, well, it's all shared.
You know how to negate an implication?
I mean, you wouldn't want to tell the
Oh,
quiz.
An
yes.
if-then statement?
That's
Oh,
easy.
yeah, that's what.
All right, Eleanor. How do you negate P implies Q?
Wait. I just learned this like last week, but it was a long time ago.
Last week was a long time.
Yes, it was.
All right. While Eleanor's thinking about that, let's talk about polynomials, because this is what we're going to be doing the rest of the semester. So this is a short packet. There's really one 4-part theorem that I'm not going to prove because all the parts are really easy and straightforward. I'll prove part of it, fine. But it's just say polynomials over an integral domain behave the way you expect polynomials to. And then,
I have to look at my notes.
okay.
I'm just trying to figure it out.
Main thing I want to do in this packet is we're going to prove that if you take a field and you take a polynomial ring over that field, you necessarily get a Euclidean domain. That's kind of a key result that we're going to be using a lot going forward, the fact that polynomials over a field always give you a Euclidean domain. Just like how we said, this forms a Euclidean domain, where basically when you say B has to be smaller, or R has to be smaller than B when using the Euclidean algorithm, R had to have a smaller degree than B did. We're going to generalize that to an arbitrary field. But first I'll mention some stuff. So if D is an integral domain with polynomial ring D of x, then D of x also has to be an integral domain. Nice. Fairly straightforward to prove. You multiply 2 polynomials. The only way those are going to cancel out and give you 0 is if you have non-zero term from D multiplying together to give you 0. I don't feel like writing that one out. If f and g are elements in the polynomial ring, then del of f plus g is less than or equal to max of del f and del g. Oh my gosh, we're taking partial derivatives in here? No, what do you think that means in this context? If I were to say something relating to adding two polynomials is less than or equal to the maximum of thing of first polynomial and thing of second polynomial.
Degree.
Yeah, it just means degree.
Oh.
I don't know why the book uses that terminology, but that's the book shorthand for degree. I would just write out deg if I had written the book, but that's just me. I mean, it is shorter, so.
Or just
Turns out if you add two polynomials, the degree of their sum is always less than or equal to the maximum of the corresponding degrees. So what would be an example of two polynomials we could add whose degree is strictly smaller than the degree of the things we're adding?
You could do x squared minus, or x squared plus negative x squared.
X squared plus negative x squared. Yeah. X squared plus negative x squared and get 0. This is going to have degree 2. This is going to have degree 2. What's the degree of that one?
Oh, negative infinity.
There you go.
Negative infinity.
Why negative infinity?
Because that's what it needs to be in order to avoid having to treat 0 polynomial as a separate case in like every theorem involving degrees.
Degree negative
Because
infinity
x to
times
the
degree
negative
anything equals
infinity is-
degree negative
For instance, part C of this theorem would break down if we said the 0 polynomial is degree 0. Which says that if you multiply two polynomials, the degree of the product is equal to the sum of the degrees.
Because 0 times 0 is always
Because otherwise we could say degree 0 times a degree 4 polynomial would be 0 times degree 4 thing, which would be 0, would be a degree 4 thing, which would be bad. But saying negative infinity is equal to negative infinity plus 4, that's totally fine. Yeah, adding 4 to negative infinity, of course you'd get negative infinity. It's more of a convention than anything else.
No makes sense.
It basically is because if the degree of 0 was anything else, theorems like this one would need like a special case, or like all non-zero polynomials, and just be able to make general statements. We like saying that.
Is it sort of the same thing of why we have like factorial of 0 is equal to 1 kind of thing?
Kind of, yeah, because it ends up being useful and avoids having to like break up into special cases otherwise.
So the little fancy D-looking thing just means that you're gonna take the end degree.
Yeah. So degree of a polynomial meaning the highest power of x that shows up on a term with a non-zero scalar attached to it.
So x to the 4th plus x to the 3rd will be 4.
Yep. Yeah, you just take the biggest power of x that shows up. And no, saying, there's a 0x to the 5th there, why isn't it degree 5? On a non-zero term, that's the degree. If you actually look at the book actually defines polynomials in a really weird way. And by weird, I mean rigorous. But rigorous involves doing things like saying, oh, it's like you define a sequence coming from that from D, and you identify a polynomial with that sequence, assuming that sequence has only a finite number of non-zero terms. And it's actually really interesting the way the book defines polynomials. But practically speaking, you all have worked with polynomials in a different way for a very long time, so I'm just going to go with what you know. And finally, part D. The units in D in the polynomial ring D of x are precisely the units in D. I'll prove this one, because this proof actually does rely on the fact that we're working over an integral domain at some point. So let's suppose that the degree, spoiler alert, degree gets involved. Suppose we have two polynomials, f of x and g of x, in our integral domain, where f of x times g of x is 1. And our goal is going to be to show that f of x and g of x then necessarily have to be elements of D specifically. So the only way to multiply two polynomials and get one is if both f of x and g of x are themselves elements in D. Okay, so what we're going to do is we're going to take the degree of both sides and say that then the degree of one, which should be equal to the degree of f of x times g of x, should be equal to the degree of f of x plus the degree of g of x from part C of this theorem. Question. What's the degree of 1? The constant polynomial 1? Eleanor?
0.
Give me 0. The degree of any constant term. Oh, look at me. I started writing on deg, even though in my notes I was using del because that's how I'm used to thinking about degree. Would you all rather I write notes and then would you rather I write deg so that it kind of makes more sense intuitively, or would you rather I write del so that it matches up with the book?
Could you alternate?
I refuse to do that, no.
Could you
This is a one-time choice that will affect the rest of the semester.
could you write del and then EG so that we can have a compromise?
Oh.
No.
No, just deg.
I would prefer
Just
a little
deg,
degree sign
yeah.
actually, but
I'm
You prefer what?
I like
Like
a
the
little
little
degree sign.
symbol?
Yeah, a little
Oh my
sign.
God.
No, because that has
awful.
geometric implications I don't want to get
Not even
into.
before the number.
How about just
Yes, it does.
EG?
I
You don't offend
regret asking.
anybody.
Okay. We're going with
Deg is
deg.
better.
Alright, we're going with deg from now
Oh,
on.
gosh.
So 0 is equal to the degree of 1, which is equal to the degree of f of x plus the degree of g of x. So, degree of f of x and g of x add up to give you 0. What does that tell you about the degree of f of x and the degree of g of x?
You can't have negative degree except for 0.
True, but can f of x and g of x be 0?
No.
Not if they multiply to give us 1. And no, I'm not writing a special case for the trivial ring, if someone asks. F of x and g of x can't be 0, because otherwise there's no way for them to multiply to 1. So we know these degrees are not negative infinity. So these have to be non-negative integers. What's the only way for two non-negative integers to add up to 0? I see you, Lincoln.
No, they have to both be 0.
So this tells us that the degree of f of x equals the degree of g of x, which is 0. And what does that tell us about f of x and g of x? They're what?
They're constant.
They're constants. So in other words, they lie in which ring?
D.
They lie in D, which is what we wanted to prove. Yeah. Because the only elements in the polynomial ring that have degree 0 are the constant terms, meaning ones that lie in the ring of coefficients for the polynomial ring. Any questions or comments about that? So, I like this one. I thought this one was interesting enough to include. The first three, they're all, parts A, B, and C are in the book. They're not particularly exciting. They're things that you've been dealing with your whole life with regards to polynomials, just generalized different ones. Yeah, Matthew.
How can we make the jump that the degree of f of x times g of x is equal to the degree of f of x plus?
By part C of this theorem.
Okay, so we're not.
I'm not proving part C doesn't mean we can't use it in order to prove a later part in the theorem. So I'll say by C here. And I mean, if you think about your intuition with regards to polynomials, that's how polynomial division works. That the leading term of f of x times g of x is just leading term of f of x times leading term of g of x. And then how do you multiply, like, if that's like 2x squared and 3x cubed, or your leading terms, when you multiply, you actually add the exponents. So
Yeah.
you add the degrees of the two things to get the degree of the
Like logarithms.
like logarithms. I will note, part C doesn't work in a non-integral domain, because if you're working over z mod 4z, you could say something like the degree of, you could say something like 2 bar times x squared, that's a degree 2 polynomial, times 2 bar x cubed. That would have degree 2, that would have degree 2. What do you get if you multiply these things together?
Degree 3.
0?
Good.
Yeah, negative infinity. Because 2 bar times 2
Right, that should be degree 3.
Yeah.
Oh, yeah. Oh, that's what you meant degree 3. I'm like, how are you getting 3 out of this product? Yeah, you're right. So here we would have a case where if we weren't working over an integral domain, part C would very much fail. Because you could have, because the leading term, well, because you could have leading term of the product is not just the product of the corresponding leading terms. If the product of the corresponding leading terms came out to 0. You do need an integral domain for that part. Otherwise, you get just another less than or equal to, like it sucks. Questions or comments? Oh my gosh, my voice is doing all sorts of things in this class. All right. In that case, let's prove our big theorem. K is a field, then its polynomial ring is an integral domain, or is a Euclidean domain. Or it's an integral domain, it's not easy.
I mean, if it's a Euclidean domain, it is an integral domain.
Well, yeah, that's why I'm saying it's a lot easier to prove it's an integral domain. Okay. Then the polynomial ring is we already know K itself has that all fields are Euclidean domains. We proved that a couple weeks ago. We've already proven that K itself as a field would have to be a Euclidean domain. But this is proving that the polynomial ring over K would have to be Euclidean.
You can also use all of the first.
You can also use all of the first theorem. Wow, that might be useful at some point. So, how are we doing this? So, who here has seen mathematical induction before? I was gonna say, I imagine most of you, like a lot of you did that for the last part of the question 3 on homework 1. So I figured most of you had. Glad to see that, because we might be needing a little bit of induction at some point here. All right, so here's what we're doing. We're gonna let K be a field. And we're gonna let F and G be elements in the polynomial ring with G not equal to 0. All right, so what's a Euclidean domain again? So Euclidean domain, you might remember, is when we say given any A and any B, or in this case F and G, in a Euclidean domain where the G term here is non-zero, we should be able to find some Q and some R term coming from the ring where what happens? A equals QB plus R, where R is somehow smaller than B. So let's write that out. Our goal is going to be to find some elements Q and R, and yes, they will be polynomials, such that A is equal to QB, or QG. You know what? I'm just going to use B, because otherwise you all are going to start complaining that my Q's and G's are impossible to tell apart. I'll just do. A equals QB plus R. The book uses it, but the book can get away with that because it's typed and not, my handwriting is not.
Did we get confused?
Your B's
It was
are
the
rotation
A
and
and the-
Q's.
A?
Oh, it was A and Q.
Yeah, it was
Well, you're
A
gonna get my
and
Q's and B's, or Q's and G's confused too. I just know it.
We should do A and G.
No. A equals QB plus R with something of R has to be less strictly smaller than something of the B term. So, what do you think the something is going to be? What's going to define our Euclidean norm? Andrew?
Degree.
It's going to be incorrect. It's not degree.
That was the reasonable guess.
But, we'll go with that for now.
Oh, wait.
What?
But it's not gonna be degree because degree of 0.
Because we need that, because if you remember, part of our condition is we need delta of 0 is 0, and 0 is not equal to negative infinity. But we're going to get around that at the end by just taking 2 to the power of degree.
Okay.
And that'll satisfy all the same stuff. And have 2 to the power of negative infinity. We're going to hand wave that away and say that's 0.
Nice.
So essentially, yes. Essentially, it is going to be degree. Technically, we need 2 to the power of degree. But that doesn't really change anything other than the fact that that's what we need to map 0 to 0.
You just showed us the definition of the degree function
It's a
with
little
this, so
circle
we're gonna
that
use it.
has these edge cases.
I just need what?
You just told us the definition of the degree function before, and then just decided to change it on a whim or a proof.
What did I wait, I
You changed what it actually means to like have a degree, because you said 2 to the whatever we have.
No, I'm just going to say delta of a polynomial, the delta that's necessary to define our Euclidean norm is going to be 2 to the power of degree of f.
Oh, let's call that delta.
We're not calling this delta because this doesn't work as our delta, is what I'm getting at.
What if we just say it's del of r?
What if we what?
What if we define del of r as 2 to the degree?
Okay, moving on. Look, this part's going to be messy enough because I have to swap all my A's and B's with F's and Q's on the fly, and I also have to swap all my del's with degs. So.
Just start using Cyrillic letters, I don't know.
Alright, so this is our goal. We're given some A and B. B is non-zero. I know, we have too much fun in here. We want to find some Q and R so that we can write A as being equal to QB plus R, where the degree of R is less than the degree of B. And even though degree doesn't quite do what we want it to, we'll just make that slight adjustment at the end and everything will still work out nicely. Alright, so, first things first. If the degree of, oh gosh, it's going to confuse me so much. I'm going to have to rewrite this over the weekend. The degree of A is 0, then we're done. Because we can just have B be equal to, or we can just have Q be equal to A over B, and yeah. So if degree of A is 0, then we can have Q be equal to A over B, and let R be equal to 0.
B over A? No, A over B. But what if B is not?
Degree of B, sorry, degree of, hold on.
Yeah, no,
Okay.
Gosh, like I said, this completely changes like everything in my notes. Now I need to take it up. So we need the degree of F, which we're now letting F be equal to A. A is 0. Then we can let Q be equal to A over B. But B doesn't necessarily have an impact. Wait.
But don't, okay, in this, do we also assume that the degree of A is greater than
How are we gonna do homework?
We're going to need to, yes. Well, specifically, we're going to assume separate cases. Because if the degree of B is greater than the degree of A, then we'll just let A be equal to R and Q be equal to 0. So, so the case where A has strictly small, or the case where A has degree smaller than B, we can handle pretty easily. If I'm looking confused, it's because it's my 3rd consecutive class, and I'm getting tired, and because this is a complicated proof, and you're asking me to change the
So if
limitation.
A has degree smaller than B, then just let Q equal 0 and R equal A, right?
Yes.
So if degree A is 0, then let Q equal 0 and R equals A?
Okay, but what about
If degree of A is 0 and the degree of B is non-zero,
Yeah.
then we can do that. Otherwise,
the degrees?
Otherwise, then Q equal, or the Q equals A over B thing works if the degree of B is also 0.
Why does it have to be straight?
I tell you all what, we're gonna skip this, and I'm gonna prove this on Monday, because I clearly need to go back over this proof with a fine-tooth comb. Instead, we'll skip it and move on to kind of the rest of this last part of the packet, finish that off, and then we'll do this proof on Tuesday after I've had a chance to actually go through, rewrite it, and fix all these bugs, which apparently I didn't do my first time going through.
No, I think you're right with
The degree of B is 0.
Because technically, I think I didn't include enough cases.
If the group do this.
Hey, let's assume this for now.
Yeah.
So what can we conclude from this? Well, we can conclude polynomial rings over a field have GCDs. I apologize. I'm starting to feel like Eleanor here. So, if K is a field, then the polynomial ring over K has to be a UFD. It has to be a PID, because all Euclidean domains are PIDs. It has to be a UFD, because all PIDs are UFDs. It has to have GCDs, because Euclidean domains have GCDs. We proved that when we first talked about Euclidean domains. And it has to be the case that it has the PID property that a polynomial over a polynomial in such a ring has to be irreducible if and only if the polynomial ring modded out by ideal generated by F is irreducible. Let's do an example. I feel confident I can handle this. I mentioned this to you last time. I claim this has to be a field. Why? Because x squared plus 1 is irreducible as an element of the real polynomials. Question is, what is it isomorphic to? Which field? Int x squared plus 1 is important. Lincoln?
I don't remember. You did this. You showed this the other day, and then
I did. I'm seeing who's paying attention. Eleanor?
I mean, based on how the homework was looking, I'm guessing it's r joined with x squared plus 1.
Oh, no, wait.
No.
No, not that. I think that's not a field.
So
Oh.
don't we know in this case that the kernel of whatever it's going to be isomorphic to is going to be x squared plus 1?
The kernel of, we're going to have a homomorphism from real polynomials to whatever this field is, and the kernel is going to be, made up of ideal generated by x squared plus 1. So polynomials that are multiples of x squared plus 1.
I'm thinking just R joined with I.
R joined with I. That's a funny way of saying the complex number. Yes, that
You
works.
could say that, yeah.
I mean, these are the same thing. So.
I'm not wrong.
This is true. You are not wrong in saying that. So let's prove that. So
Wait, what? No, it's the same. Remember the
No, I
definition of
remember,
a joint?
they are this set is defined to be literally all elements of the form A plus BI, where A and B are real numbers.
Why is Archer lecturing us on how the joint thing works?
I must be really having
I
an off
used-
day for that to happen.
I was the guy who used to hate this notation, and now I know it.
Oh, now he loves it.
Unless it's rational.
It's like a love hate.
Oh, unless it's the thing we're going to be doing the most
Wait,
later in the
what?
semester.
No, you can't
Okay.
say that. It's so mean.
Okay, so how are we going to prove this? What theorem? Fit. Let's. All right, we're gonna have fit. So
What
we're
is
gonna define
happening?
phi as a function from thing we're modding out by to the complex numbers, and we need its kernel. We need this to be a homomorphism whose kernel is things that are a multiple of x squared plus 1.
What if we map x to I, so like x squared plus 1 equals I squared, or we map to I squared plus 1?
Be defined by phi of f of x equals f of I. So like 5x squared minus 6x plus 1 is going to map to 5i squared minus 6i plus 1. Yeah, what you were suggesting. Alright, then phi's homomorphism, I'll let you all check that.
Oh.
Let's check the image of phi. Is is complex numbers. So given any element to the form a plus bi in the complex numbers, what would be some polynomial that'll map to a plus bi? I'm not asking Lincoln because he'll give me something more complicated than it needs to be. I don't want to ask either of these guys, but I'll ask Seamus.
Wow. Bx plus a.
Oh, thank you. All you did was change the order around, and I don't care about that. See, if I asked Lincoln, he was going to say something like a plus bx plus x squared minus plus 1 or something. All right, so image that is 6. All right, let's look at the kernel fee.
Your confidence in my ability to remember my complex analysis is flattering.
Considering you're writing a poster on all the complex analysis you did last summer right now, yes, I have some faith in that. Apparently I shouldn't. So let's look at the kernel. So the kernel, by definition, is the set of all f of x satisfying f of I is equal to 0. F of x, I should say, real polynomials. What do we know about real polynomials that when you plug in I, you get 0?
Well, I squared is -1, so if you have x squared plus 1, you're gonna get a 0.
Do they all necessarily have to be multiples of x squared plus 1? Anything that is a multiple of x squared plus 1 would certainly have it, that if you plugged in I, you'd get 0. But does that work in reverse? Wouldn't that be nice? Well, how about this? That's the same as saying the set of f of x such that x minus I divides f of x.
But x minus I is not an element of the real polynomials.
So what is that? So yeah, it doesn't mean but that doesn't mean you can't plug in I and get 0 in the complex numbers. Like just because you give me a real polynomial doesn't mean I can't plug in I for x and end up with 0 by doing algebra in the complex numbers.
And so should we note it also means have x plus I as a factor?
Which is equal to the set of all f of x such that x minus I times x plus I has to divide f of x. Which is the same as the ideal generated by x squared plus 1.
So can you add the x plus I because that is a...
So, Dr. Gerstle, where did the x plus I come from?
Yeah.
This is related to this in a way that we're going to prove later in the semester.
Oh.
It's going to involve something called the minimal polynomial of a field extension, which basically says x minus I can't divide, which is a more general version of something that basically says x minus I can't divide a real polynomial. Yes, Emily Rose, I is not in the reals. X minus I can't divide a real polynomial without x plus I also necessarily dividing it. Something we'll prove later in the semester. This one, though, we'll prove now.
That just, wow.
Well, and by now I mean in the next page of the packet. The fact that x minus I is divided f of x not divided.
Oh, I wasn't raising my hand.
Well, you were saying something.
Oh, it was important.
Okay then. And then by fit, we get so that would be how we could prove this a little bit more formally. Is technically we need a result from later in the semester to make this a formal proof. Otherwise, we just get that ideal generated by x squared plus 1 is a subset of the kernel and not necessarily the full kernel. But that's going to come from a later result.
That later result, is that like a generalization of things that conjugates work?
Yes.
Okay.
Think complex conjugates for now and something else later.
This really is an abstract algebra.
This what?
This really is the abstract version of algebra too. Because that's like,
Yeah.
yeah.
That's what I said. Let's prove this result, that if f of I is 0, x minus I has to be a divisor. So That's actually much easier to prove, and I have more confidence in my notes for this proof. It's a consequence of something called the remainder theorem. Where the remainder theorem says we're going to let K be a field. We're going to get fancy and let alpha be an element of K. And F not equal to 0 be an element in the polynomial ring over K. Then the remainder, when dividing F by x minus alpha, is F of alpha. And then as a consequence of this, basically by just assume in the case where f of alpha equals 0, we get the factor theorem that says alpha is a root of f if and only if x minus alpha actually divides f. All right, so here's our proof. So given all this stuff, I'm just going to write given the above because we don't have much time left. We know there exist Q and R elements in our polynomial ring such that f of x is going to be equal to x minus alpha times q of x plus r of x, with the degree of r of x being less than the degree of x minus alpha. So we're essentially just applying the Euclidean algorithm here. We're applying the Euclidean algorithm where f is taking the place of, not that f, where f is taking the place of our a and x minus alpha is taking the place of our b. So we're assuming all that stuff I failed to prove utterly earlier actually works for this. So far so good? What's the degree of x minus alpha?
1.
If the degree of r of x is less than 1, what does that tell us about r of x?
It's constant.
Yeah, it's constant. Possibly 0 if the degree is negative infinity, which I guess is less than 1. But it could also have degree 0 if it's a non-zero constant. Either way, r has to be constant. So then r is a constant. So we can stop writing r of x and just say literally little r. So subbing alpha for x gives us the formula into this equation. F of alpha is equal to alpha minus alpha times q of alpha plus r. And what does that right hand side simplify to? R. So f of alpha is equal to our remainder term. In other words, when we divide f of x by x minus alpha. And then I'll mention as a corollary, just take the above equation, replace f of alpha with 0, and you get 0, 0. You get, here, I'll just say this. In this equation, f of alpha is equal to 0 then becomes the same as saying r is equal to 0, which is the same as saying f of x is equal to x minus alpha times q of x, which is the same as saying x minus alpha is a divisor of f of x. Boom, we've proven the factor theorem too. basically saying x minus alpha is a divisor of f of x if and only if, when you plug in alpha for x, you get 0. It's like a theorem you probably saw in like high school sometime. Like, if you can plug in 2 for x and get 0, then that means you can pull out a factor of x minus 2 from your polynomial somehow. Works over any field, turns out. Alright, get out of here. We come back Tuesday, I'll actually prove the theorem. Sorry about that today. And then from there, we will move on to start talking about properties of irreducible polynomials. And how can we check to see if something is irreducible other than guess and check? Y'all have a good one?